Hello and welcome to 5.2. We're going to start talking about the characteristics of polynomials. We did the math with them. Now, what does all that stuff mean? So let's jump into it, learn a little bit more about polynomials. All right, as normal, we got to start with a couple of vocabulary words. So as we've been talking about, been talking about polynomial functions, which you should be pretty familiar with, but the technical mathematical definition looks something like this, and that is f of x equals a n x to the n plus a minus n times x to the n minus 1. Basically what this means is you've got a number times x to a certain power plus another number times x to a power lower than that one, so on and so forth for however many x's that you have. So if we're going to look at this part right here, so the coefficients, these are all the coefficients. So that's the big number in front of the variable. So that's that guy right there. And notice that this is not 0. So if it was 0, then that whole x term would just go away, and we wouldn't worry about this thing. We would just start over here. Also, let's see here, and n is a positive integer. So that's these n's right here. More specifically, no negative exponents. So we don't want negative exponents in there. We would just express those as a fraction or something like that. So if we look at a of n, so that is this guy right there. So this is what we call a leading coefficient. A leading coefficient. And it can help tell us a little bit more about kind of the general shape and or what we're looking for. So just note that is the leading coefficient. So then as we get down here, we start talking about degrees. I think we've mentioned this before, but a certain degree polynomial is basically the highest exponent next to a variable that we have in that function. So for example, here we don't even have a variable, so our variable has a 0 on it. So this is what we would call a 0 degree polynomial, and its leading coefficient would be this guy right here, so it would just be 4. Okay, so if we wanted to go down the line, so we look at this thing right here. So this is a first degree polynomial, and the number associated with that highest degree variable is going to be a -5. So that's this guy right here. So hopefully you've kind of gotten used to the pattern here. So this is going to be a second degree polynomial with a leading coefficient of 12. This next one's going to be a third degree polynomial, leading coefficient of -1. So there is no number there, but there's a negative sign, so it's an insinuated -1. Fourth degree polynomial, -3. And then a fifth degree polynomial with a leading coefficient of 9. So nothing terrible, but we're just getting used to the different terminology that we're going to use. Okay, this should be another little bit of a review. Just to go over some of the parent functions that we might be dealing with. So if we have a constant, that's going to look like f of x equals a number. We use c for a constant. That's just going to be a horizontal line. Generally, they'd be flat, but my artistic ability is terrible. So then if we have a linear equation, so we're going to have f of x equals x. So we'll have some x, but just it's a first degree polynomial. And this is just your standard line. Okay, we've done a lot with quadratics. F of x equals x squared. So hopefully by now you know that that's not quite a v, and that should be a little bit rounded. And cubic, that's going to be f of x equals x cubed. So this is where we start to get a little fun. This is going to be a little wavy. Kind of like that. And then as we go down the line, we've got quartic, which is going to be f of x equals x fourth. So that's the fourth degree polynomial. This is going to kind of look like a quadratic, but it's actually a little bit more wider, I guess. And then we've got a quintic, which is also going to look very similar to the, f of x equals x to the fifth. And the quintic, that's going to be x to the fifth. It's going to look very similar to the x cubed one. Again, going in two different ways. So hopefully you see a pattern here, maybe? Let's explore that pattern. All right, so let's talk about end behavior. So the way this part works is just you can shove all these into your calculator and you can look at the graph and you can kind of figure out what the end behavior does. So I kind of did that and I made these little quick sketches, so at least we can just have a conversation about end behavior. So if we look at this first one, it's to the fourth degree polynomial and it kind of looks like this. And again, I just put it into my calculator and looked at the picture, but it's enough for us to go, so as x approaches infinity, f of x is going to approach positive infinity. As x goes to the negative side, it's still going to go up. So if we look at it, here we go. So if we look at it, it's going up in both directions. Okay, so if we look at number 2, it's an x squared. It's a negative x squared, so we know it's going to be a parabola. So this is in my way. And so that means that our end behavior, they're both going to be negative infinity as it goes to the positive and the negative. Okay, so moving right along, we've got our 2x cubed. And again, we look at this as x approaches positive infinity, it's going up and up and up all the way over here. And then as x approaches negative infinity, it's going down. So here we can write as x approaches positive infinity, f of x is going to approach infinity. And then as x approaches negative infinity, f of x approaches negative infinity. Okay, so hopefully you're picking up on a pattern here. Anyway, continuing our pattern, we have a negative x cubed. Looks similar to this, but just flipped on the x-axis. So as x approaches positive infinity, it going this way, it's going down. So let's move this out of the way. So then that's going to be our negative infinity. And then as x approaches negative infinity, it's going up. So it's approaching positive infinity. So then number 5, this is a normal parabola. Look, there's a negative sign right there. So both of, as x approaches both positive and negative, so the further out left we go, the further out right we go, it's all going to be the same. It's going to be negative infinity, negative infinity. So then over here on 6, here's our little graph there. Move it out of the way. And again, as x approaches positive infinity, as we go to the right, it's going up. And as we go to the left, it is going down. So have you caught on to the pattern? Let's look at it. So when you look at the degree polynomial, you can tell the degree polynomial and the coefficient, the leading coefficient, you can tell the end behavior of the graph. So if the positive leading coefficient, if the leading coefficient is positive and it's an even degree, they're both gonna go up. So we can write a little arrow like that. And if it's an odd degree, as you go to the left, it's going down. As you go to the right, it's going up. So then if the leading coefficient is negative, it's just the opposite of all of that. So it's going down, down, and then, oh, I can do better than that. Up, and then down. So with that pattern, we can actually use that to start to figure stuff out about some of these more complicated polynomials, like all this stuff up here. So let's try some out. So number 7 says determine the sign of the leading coefficient and whether the function has an even or an odd degree. So we can use that pattern that we just talked about, and we can figure this out. So first of all, both of the signs are, both of the end behavior is going down. They're going the same direction. So I know that it is an even degree. So, like x squared, x4, x 6, x to the 6, something like that. We know it's not x squared, but anyway. So then, since it's going down, we also know that the leading coefficient is going to be negative. So I'm going to write negative. Can't spell negative. So we know the leading coefficient is negative, we know it's an even degree, and we can kind of tell that it's not an x squared, because we know what an x squared looks like, and this is much more complicated than that. But if we move on to number 8, we can do the same thing. Because the arrows are going opposite directions, I know that it is an odd degree polynomial. And based on our pattern, the left one's going down, the right one's going up. We know that that's kind of like the normal case or the positive case. So again, this is just some characteristics that we can look at that can tell us a little bit more about the graphs that we're messing with. Okay, so some of the next vocabulary words we got to talk about is turning points. So turning points is a term, a phrase that we use a lot when describing graphs. And it's a characteristics of the different graphs that we're going to have, like how many turning points that a certain graph has. And it's, kind of obvious, like the turning point is where the graph turns. So, or switches directions. So the points at which the polynomial function switches directions. And that's, going from increasing to decreasing, or from decreasing to increasing. So that's kind of why we talked about those earlier. Whenever it changes direction like that, we call that a turning point. So when we have a turning point, and it is higher than any other nearby points, it is called a relative maximum. So if we look at the graph over here to the left, this is a relative maximum. So we call it a relative maximum because it's higher than all of these other points here, but it's not the absolute maximum because this goes on forever. So there's points up here that are even bigger than that maximum. But especially in like real world scenarios, when you're looking at costs, profits, things like that, you're going to be more interested in this kind of stuff. If you're like doing research and like, oh, what made it change? Maybe our profits were great here, but then COVID hit and then our profits dropped, and then COVID got better and our profits are skyrocketing. Whatever the case may be. But here we call that a relative maximum. So conversely, the opposite, if we have something that's lower than everything around, it's going to be a relative minimum. Relative minimum. And then those are both different types of extrema. So an extrema is the next kind of vocabulary word that we talk about, if I can spell it. So maximum and minimum values are called extrema. So, these are both types of extrema. What specific types of extrema are they? This is a maximum, relative maximum. This is a relative minimum. And again, turning points define where the function is increasing or decreasing, or when it changes. and it gives you the minimum on the calculator. So we're just going to round it to the nearest hundredth. So our minimum is going to be it's going to be 3.29 comma negative 4.30. And remember, that's a point, but that's the point where our relative minimum is on our graph. Okay, we've got our relative maximum and our relative minimum, and our graph kind of sort of looks like that. And then from there, we can actually give a more precise intervals for increasing and decreasing. So, our increasing intervals is going to be right here, where it's getting bigger up to this maximum. So that means it's going to be negative infinity to our x value is going to be 0.71. So remember, this is an interval, whereas this is a point. I know they're going to look the same, but it is what it is. So then our next increasing interval, so it's decreasing all here, and then it starts here and starts increasing again. So that's going to be at 4.30 to positive infinity. And then, of course, our decreasing interval is that part right there. So that is going to be, let's see here, starting at 0.71, and goes until 3.29. So it's easy to get confused here because all of these things look similar, but these are two intervals. This is a single point. So this is a point. The blue is intervals. So try not to get them confused, but let's do a couple examples and you'll be on your way. 8, 4, and then the next one is from 0 to positive 1.09. So again, these are characteristics you're going to be looking on the calculator a lot, at least for these. Okay, at this point, we're just looking at our calculator and trying to figure stuff out based on that. So try numbers 3 and number 4 by yourself. Draw a little sketch, and I'm going to do the same. I'll post the answers here in just a minute. So pause the video, and we'll compare answers. Okay, here's what I got. This is kind of a picture for number 3. Our domain is all real numbers. Our range, got you on that one. It starts from this point and goes down. So don't get caught on that. No, our ranges are no longer all real numbers. So then we've got a relative maximum, minimum, maximum. So we've got our two maximums right here and our minimum. And then our two end behaviors, it goes down on forever this time, this way, goes down forever this way. So we've got negative infinity, increasing interval, decreasing interval, decreasing interval. So that's what we got for number 3. Number 4, because it goes off into both directions, our domain and range are both all real numbers. We have a relative maximum right there, relative minimum right there. Again, just use the calculator to get that. We've got our end behaviors. So as we go to the left, it goes down. So that's this guy right here. As it goes to the right, it goes up. That's this guy right here. Our increasing interval is right here and right there. Notice we have our infinity and our other infinity. And then our decreasing interval is just the one right there in the middle, which is just like that. So, did you get the same thing I did? If so, good job. Either way, I'll see you in class.